Surface supplied diving is a mode of diving that is used as an alternative to scuba diving. While the term surface supplied might lead you to believe that the breathing gas is supplied from the surface, in saturation diving applications, an undersea habitat essentially provides a new surface from which these types of diving operations originate. Surface supplied diving is a form of diving in which the breathing gas is supplied from the surface rather than from self contained equipment. In scuba, the breathing gas is supplied to the diver by a regulator attached to a cylinder on his back. In surface supplied diving, the gas is delivered to the diver from the surface by a hose attached to a helmet or a full face mask. The most obvious advantage of using surface supplied diving over scuba diving is that the diver is provided with a continuous breathing gas supply. This allows divers to maximize their bottom times. Since breathing gas is supplied by a hose, a direct link from the surface to the diver is established. In addition to the gas supply hose, a strength member is incorporated to form what's known as an umbilical, a hardwired communication line, power for lighting and cameras, and other assets can be incorporated into the umbilical to help the diver work more safely and efficiently. Even if electronic communication malfunctions, divers and the surface can communicate by using line pulse signals. Primary disadvantages involve the gear itself. Surface supplied diving requires a large amount of gear, both on the surface and the gear that the diver is required to wear. And since the breathing gas is supplied by the surface, a diver's mobility and range are also restricted by the umbilical's length and drag weight. The minimum equipment requirements for surface supplied diving greatly exceed scuba diving operations. However, surface supplied diving provides a distinct advantage over scuba for operations that require an unlimited gas supply and communications. The topside air supply system is equipment intensive. Any system used must be able to support the requirements of all divers, taking bottom time and decompression time into consideration. The topside breathing gas can be supplied by a low pressure compressor or by multiple cylinders of high pressure gas. This Mk3 system consists of 12 300 cubic feet cylinders that are divided into 4 racks of 3 cylinders to make them more portable. In comparison, typical recreational scuba divers carry one cylinder consisting of 80 or 100 cubic feet of gas. A breathing gas manifold or console is used to monitor and control the supply and pressure of gas to the diver. The console consists of a pneumofathometer that keeps track of a diver's depth and a hand-loaded regulator to determine how much breathing medium is pushed to the diver and at what pressure. Each diver is differentiated by a different color umbilical, red, green, and yellow. There is also a communications box that is hardwired to the divers through cables in the umbilical. This table serves as a guide to the operator. For example, if divers are diving between 0 and 60 feet, the operator needs to ensure that the regulator is set to 150 psig. If you remember the pressure conversion table in Module 3, feet of seawater times 0.445 equals psig. At 60 feet of seawater, psig is approximately 27. That means that there is an additional 123 psi pushing against the water pressure surrounding the divers. This extra air pressure helps the divers expand their lungs much easier, needing less respiratory effort in order to breathe. This table is based on the same concept as the previous one, but it reflects a different standard. As we move from the surface-based equipment to the diver, typical equipment worn by a surface-supplied diving aquanaut is shown here. This surface-supplied diving aquanaut is using a SS-37 diving helmet. Major diver assemblies consist of the helmet or full face mask, an umbilical, emergency gas supply, and a harness. We will focus on two diving helmets in particular, the Superlight 17 and the stainless steel 37. Both helmets have similar capabilities and depth limitations based upon the standards being followed. The Superlight 17 shell is made from fiberglass with brass fittings that add balanced weight to reduce buoyancy when the helmet is filled with air underwater. The helmet provides physical protection to the diver's head, which is especially useful during salvage operations, along with thermal protection during cold water dives. The faceplate is made from Lexan that fits into a molded recess in the helmet and is sealed with an O-ring. Lexan is used because it's impact resistant, strong, durable, lightweight, and provides excellent optical clarity underwater. A head cushion provides thermal protection and reduces dead air space inside the helmet. It is snapped into the helmet and is secured to the diver's head by a chin strap. This allows the helmet to rotate with the diver's head. This also ensures that the diver's nose and mouth remain in alignment with the helmet's built-in oral nasal mask. The helmet is secured to the diver's head by a neck dam and neck clamp yoke assembly. The neck dam is a neoprene seal attached to the neck yoke that fits over the diver's head and forms a watertight seal around the neck. The helmet is then fitted onto the yoke and secured with a clamp and locking pin. Air is delivered to the diver by a demand regulator. A demand regulator is activated by the diver's inhalations, very similar to a scuba regulator. Divers control the ease at which the air is delivered by adjusting the dial-a-breath knob. Typically, a diver will adjust the dial-a-breath knob to a point where air is easily inhaled, but not to the point where air is constantly flowing or free-flowing. An oral nasal mask is attached to the regulator on the inside of the helmet. This oral nasal mask fits over the diver's nose and mouth, and as the diver inhales, negative pressure activates the diaphragm assembly that lets air in. The oral nasal exhaust valve assembly is a one-way valve that aids in removing accumulated water from inside the oral nasal mask and prevents free flow of the demand valve when the diver is working in an inverted position. Whiskers are routed along the side of the helmet to carry exhaled gas from the primary exhaust valve away from the diver's field of vision. Since the diver cannot use his hands to physically pinch his nose to equalize sinus pressure on descent, a nose block device is installed to serve this function. The nose block device is shaped like a V on the inside of the helmet that fits under the nose. A knob on the exterior of the helmet can be manipulated to block the nostrils to do a Valsalva in order to equalize pressure. The side block assembly is a one-way valve that channels breathing gas from the umbilical and emergency gas supply to the demand regulator via the vent tube. The gas supply non-return valve is a one-way spring-loaded assembly that prevents a reverse flow of gas from the helmet through the umbilical if breathing gas depressurization occurs. Since failure of this mechanism can lead to substantial diver injury or death in umbilical depressurization events, thorough pre-checks are required. The low pressure port on the side block is used for dry suit inflation when diving in cold or contaminated waters. The steady flow valve channels breathing gas to the gas train inside the helmet above the faceplate. When opened by the diver, air is directed over the faceplate to clear fogging. It also provides the diver with a way to cool off and can also be used to force out any water that may leak in from the neck dam. The EGS valve, or emergency gas supply valve, is attached to the emergency gas supply cylinder worn on the diver's back. The cylinder is always open while the EGS valve on the helmet remains closed. Should the diver lose his primary air supply from the umbilical, they would need to open the EGS valve to have access to gas inside the cylinder. The water dump valve assembly aids in removing accumulated water from around the diver's face. It is a one-way valve that opens when air pressure inside the helmet is increased when the steady flow valve is opened. Voice communication is the primary means of communicating with the surface. The microphone is attached inside the oral nasal mask, and the earphones are clipped inside the helmet shell or placed inside the head cushion. A communications whip on the helmet is attached to a comms cable integrated into the umbilical. The terminal end of the cable is attached to a communications box at the surface. Should voice communications fail, line pulse signals are a secondary means for communicating between the diver and the surface. An emergency gas supply is carried in a cylinder or cylinders on the diver's back. The size and number of cylinders need to contain enough gas to bring the diver to his first decompression stop or to the surface, and is required for all surface supplied diving operations. The EGS regulator is set at the manufacturer's recommended pressure, and an approved submersible pressure gauge must be attached to the first stage. There are a number of harness assembly types, but all basically consist of a way to attach an EGS cylinder and the associated first stage regulator, pressure gauge, and low pressure hose that attached to the EGS valve on the helmet. The umbilical consists of a gas supply hose, pneumofathometer hose, strength member, and communications cable. Cables for lights, cameras, and other assets can also be included. A spinnaker shackle attached to the umbilical gets clipped into the diver's harness so that it remains secure. Managing the umbilical is a critical skill to master for both the diver and the surface tender. Improper umbilical management can lead to entanglement or can create sufficient drag that the diver's mobility is severely limited. There are a few situations that can be considered emergencies if not addressed promptly and properly. Should the diver's helmet flood, he would first assume an upright position and open the steady flow valve. The increased air pressure inside the helmet will exhaust the water through the neck dam. After communicating with the surface and diagnosing the problem, the dive would continue if the problem was corrected. If not, the diver will be forced to terminate the dive. When a diver encounters excessive breathing resistance, the first thing he should do is report the condition. The problem may be surface-based if the console operator hasn't properly adjusted the hand-loaded regulator to determine how much breathing medium is pushed to the diver and at what pressure. If the diver has gone deeper, then a fix might be as simple as adjusting the dial-a-breath knob to decrease the breathing resistance. If the condition persists, the dive would need to be aborted. Should the diver experience umbilical gas supply failure, he would open the EGS valve, report the condition, and move to abort the dive. If the diver experiences a free-flowing regulator, the first thing they would need to do is adjust the dial-a-breath and report the condition. Since air continues to flow to the helmet, there is an ample amount of breathing gas that also serves to keep water from entering. If the dial-a-breath adjustment doesn't rectify the problem is likely to be a failure in the second stage settings, and the dive would need to be aborted. Should the umbilical become fouled or pinned, the diver would report the condition and then attempt to free the umbilical himself by retracing his route. It is important that the diver doesn't pull the umbilical or put any undue stress on it that could cause the umbilical to be cut or compromised. If the diver is unable to free the umbilical, a dive buddy or a diver deployed from the surface will render assistance. It is evident that surface supplied diving operations are substantially more involved than scuba diving operations. There are several maintenance guidelines that need to be followed, and annual, monthly, and daily checklists must be completed without fail. Prior to making a dive, pre-dive setup procedures are required for the helmet umbilical assembly and for the EGS. At the start of operations, divers move to the dive station completely dressed except for the helmet and umbilical. The tender then works through the pre-dive checklist with the supervisor. When it comes time to hat the diver, the tender will assist the diver with fitting and securing the helmet. At that point, the diver, tender, and supervisor will check the air, steady flow, and EGS valves, second stage regulator function, dial a breath, and communications. Final checks will be conducted by the supervisor prior to the diver entering the water. Once in the water, the supervisor will run through a last series of in-water checks before the diver is allowed to leave the surface. During the dive, tenders work with the divers to manage the umbilicals. As with extensive maintenance guidelines, several procedures are in place to ensure safe diving operations. Manning requirements often depend on the organization's dive standards that they're following. The minimum manning requirements listed here are for OSHA diving operations. In summary, we have reviewed the surface applied diving equipment and function, emergency procedures, dressing and tending the divers, as well as operating procedures. For more information and details, the NOAA and US Navy diving manuals have extensive sections dealing with surface applied diving.